In this video today, we are going to see about a null space and range space. But before we go to that, we'll just have a quick recap of linear transformation. Function t from one vector space V to another vector space W is called a linear transformation. If t of x plus y is tx plus ty and t of cx equal to c into tx for xy in V and c in F. Now we define the null space of a vector space V. Let V, W be vector spaces over the field F, and T is the linear transformation from V to W. Linear transformation, the null space or kernel space of T is defined by n of T. Kernel of T or null space of T is equal to set of all x in V such that T of x is equal to 0. So now this n of T is actually, it is in V. Those elements of V which gets mapped on to 0 in W, we call, when you pick up all those elements x, that you call it as the null space, the collection of all those x of V for which when you apply T, you get the vector space 0. Vector 0 is called the null space or kernel. Now range, let V and W be vector spaces over the field F and T from V to W be a linear transformation. Then the range or image R of T is defined by R of T equal to T of x. All T, when you apply x on T, you apply T, then all those Tx, whatever you have in W when you collect, that you call it as the range or image set. Now we see a theorem here. Let V and W be vector spaces. T from V to W be linear. Then n of T is a subspace of V. R of T is a subspace of W. So the first one we are going to prove it is a subspace of V. Okay. So now by definition of null space, n of T, what is n of T? Those elements of V for which T of x equal to 0 is known as the null space. Now T of 0 is 0. Therefore, this 0 belongs to n of T, the first one. Now let us consider two elements x, y in n of T. Now as they are in n of T, when you apply T, what will be the answer? It will be 0. So T of x is 0, T of y is also 0. Now let us find out what is T of x plus y. Now T is a linear transformation, so T of x plus y equal to Tx plus Ty. But just now we got Tx as 0, Ty as 0. So 0 plus 0 is again 0. So when I apply T on x plus y and I get the answer as 0, means this x plus y is in the null space n of T. So x plus y belongs to n of T. Now the next one, let me consider x belonging to n of T. We know that immediately T of x will be 0. Take a c from scalar. Let us find T of cx. But T is a linear transformation. Therefore, T of cx equal to c into Tx. Tx is 0. So c into 0 gives me 0. When you apply T on cx, the answer is 0, means this cx belongs to n of T. Therefore, one condition x plus y belongs to n of T. Another condition cx also belongs to n of T. So, two conditions for a subspace are getting satisfied. Therefore, n of T becomes a subspace of V. Same procedure, we prove that R of T is a subspace of W. Now, same pattern, this is the definition of range. R of T will have all Tx for x in V. Now, T of 0, answer is 0, therefore it belongs to R of T. Now consider x and y in R of T. Whenever x and y are in R of T, there will exist elements u and v in V such that when you apply T, you get x and y. So T of u will be x and T of v will be y. Now let us find out what is T of u plus v. Now T is a linear transformation. Therefore, T of u plus v is equal to Tu plus Tv. but tu is x and tv is equal to y. So the answer is x plus y. So t of u plus v, I am able to get it as x plus y. Therefore, this belongs to R of t. X and y are in R of t. X plus y is also in R of t. First condition is getting satisfied. Now go for the next condition. For x in R of t, c in f. Let us consider t of cu. So what is t of cu? C into tu, because t is a linear transformation, but tu by definition tu is x. So tu, I am substituting x, so it is c into x. So t of cu is equal to cx. This shows that that is also an element of R of t. So both conditions are getting satisfied. Therefore, R of t becomes a subspace of W. The next theorem. Before we go, we'll just define what is nullity and rank of T. Now suppose T is a linear transformation between two vector spaces V and W, then the dimension of n of T, you call it as nullity of T, and the dimension of R of T is called the rank of T. Okay, now V and W are vector spaces over F. T from V to W is a linear transformation. If S is equal to V1, V2, etc. Vn is a basis of V, then R of T will be equal to the linear span of T of V1, T of V2, etc. T of Vn. This is what we are going to prove. So first let us write what is given. T is given, V to W is a linear transformation, and yes, V1, V2, etc. Vn is a basis of V. Now V1, V2, etc. Vn are all elements of V. So when I apply T, all those elements TV1, TV2, etc. TVn, they will all be in the range space of T. So TV1, TV2, etc. TVn, they belong to R of T. And just now we proved that R of T is a subspace of W. Therefore, R of T contains the linear span of all these TV1, TV2, etc. TVn. So this will imply that all these ones are contained in R of T. This is our first one. Then now let us consider one W in R of T. Whenever there is a W in R of T, there will exist a V in V such that when you apply T on V, you will be able to get this W. Then T of V will be equal to V. Now V1, V2, etc. Vn, they form a basis of V. So whenever they form a basis of V, any element of V will be you'll be able to write it as linear combination of these basis elements. So I'm going to write that V in V as linear combination of V1, V2, etc. Vn. So alpha V1, alpha V2 plus etc. up to alpha Vn. Now what is W? T of V. So W equal to T of, in the place of V, I am writing this alpha V1, alpha V2, etc. alpha n Vn. Now T is a linear transformation. So all these alphas can come out and we can write it as alpha 1 TV1 plus alpha 2 TV2, alpha n TVn. This way we are able to write all these. So this shows that W, whatever you have, is in the linear span of TV1, TV2, etc. TVn. What is W? We consider W from R of T. One element of R of T we were able to consider, and we have shown that it is in the linear span of TV1, etc. TVn. Therefore, we conclude that R of T is contained in the linear span of this. Already we have proved that linear span is contained in R of T. So from these two, whenever one is contained in the other is contained in the previous one, then it means that they are equal. So R of T is equal to L linear span of TV1, TV2, etc. TVn.